Okay, so far we have learned about binary logistic regression in the sense that we said that it is binary because it has two classes, right? We have two classes, for example, cats versus dogs, and we encode them as 0 and 1, and we try to classify our data according to these two classes. But the question is, how can we do it for multiple classes then? In other words, how are we going to do multi-class logistic regression? So what is multi-class logistic regression? In multi-class logistic regression, we can have Y, or our categorical response variable, to be belonging to one of K different classes. So going back to our original example, it can be according to height, weight, and number of legs for an animal. We would like to see if it's a cat or a dog or a hen, right? So we have more than two classes. Or if you want to classify patients in having flu, cold, or COVID-19, so it's three classes also. So in multi-class regression, we still have our xi, and we are assuming that they are numeric also still, and they are augmented, so belonging to R to D plus 1. But our yi, our response variable, is a member of one of the classes. It can be class C1, class C2, etc., class CK, right? So these are K categorical classes for us. Now, when we were doing a binary logistic regression, we encoded yi's as to being 0 or 1. So that was a binary response that we had. But the problem is that with multi-class logistic regression, it's difficult when we have multiple classes. We cannot just say that it is either 0 or 1. And because it was 0-1 situation, it was easy for us to define it as a probability of being in class 0 or probability being in class 1. How do we encode our classes when we have multiple classes? So the way we do it, and it's a popular way to do it in deep learning or neural network also, is to encode the yi's using something that we call one-hot encoding. So what is one-hot encoding? We have binary vectors of length k for each of the yi's. One of the elements of this vector is for one class. And when a data point belongs to one class, that element in the vector is going to be 1, and the rest of the classes are going to be 0. So for example, we have this yi's that belong to cat and dog and hen, right? And so what we are going to have is a length 3 vector to encode our classes. And so we say for cat, we are going to go with 1, 0, 0. And for dog, the second class, we're going to go with 0, 1, 0 vector. And for hen, we are going to go with 0, 0, 1 vector. So basically, they are going to be, yi's is going to be a binary of k size, right? And similar to standard basis vectors or axes that we had, this is basically our E1, right? Standard basis vector 1, standard basis vector 2, standard basis vector 3. Okay. So our data now is going to look like this. So before, our data was like this. It was D. We had augmented. We had x0, x1, etc. xd. x0 was all ones, and each data point x1, x2 until xn were rows of our data, and these were attributes 1 to D. And then we had our class label y that was cat, dog, cat, etc., etc. Now our data is going to be represented like this. So our data is going to be augmented. It's going to have the same x's, so similar. The x doesn't change. x1, x2, xn, these are all ones. But our y is going to be, so we are going to have a matrix X still. So this was our matrix X. And for Y, when it was linear regression, it was a vector. When binary regression, also it was a vector of 0 and 1s. But here, our matrix, we have a matrix Y that, for example, cat, dog, hen, it's going to be like this, 0, 0, 1, 0, 0, 1, 1, 0, 0, etc., etc. Right? So in each row, we are only going to have 1, 1. Okay? Just a representation of our data. Now, so how are we going to do something similar to binary logistic regression in multi-class case? We are going to use an idea that is similar to sigmoid. So again, what we are trying to do is that we want to find the probability that our yi is from class Cj now. So instead of 0 or 1, we say class Cj given our data point xi. And that we can define a function pi, but for each class, we are going to define a function pi j for class Cj of xi. So probability. So we are going to have this for all of our classes. We are going to define this probability mass function for all of the classes. So j is actually a value from 1 to k. So we define pi sub 1, pi sub 2, pi sub 3, until pi sub k, 1 for each class that we apply over xi. And because we have this probabilistic view, what we need to have is that, well, we need the summation of probability of yi being belonging to class C1 or C2 or C3, etc., until Ck should be equal to 1, right? It's a probability. So the summation of pi j of xi, j is equal to 1 to k, should be equal to 1 for all of our data points. So our function pi should be defined, pi sub j should be defined such that the summation of pi sub j's are going to be equal to 1. And so that it remains a probability. So our goal is to find a good pi sub j function for all of our class. Actually, if you remember from the binary situation, we can define it like that also. So we had the probability of yi being equal to 1, which was pi of xi, and the probability of yi being equal to 0, which was 1 minus pi of xi, right? But we can say that, okay, this is pi 1 of xi, this is pi 0 of xi, and also pi 1 of xi plus pi 0 of xi is equal to 1. In general, also, so it's basically a multi-class extension of what we had in the binary situation. That's what I'm trying to say. Also, because we know that all of these are going to sum up to 1, in practice, we really do not need to define pi of j for all the j's 1 to k. Why? Because if I know pi 1 and pi 2, pi sub 2, pi sub 3, etc., etc. until pi sub k minus 1, I can easily calculate pi sub k from all of these, right? So I can conclude, because they sum to 1, that pi sub k is equal to 1 minus pi sub 1 plus pi sub 2 plus etc. plus pi sub k minus 1, right? So similar in the binary case, when I knew pi xi, pi of yi being equal to 0 was just 1 minus pi xi, right? Okay, so basically that's what we have. That's our definition of the problem, and what we are looking for is to find a good pi j. Now, we want this whole thing to look like our binary logistic regression, right? So similar to the binary logistic regression, what we can do is that we can assume that our pi's are somehow have a sigmoid-like relationship with W transpose Xi's. But these W's, for each class, we are going to have one set of weight vectors, a different set of weight vectors. So basically, we assume that pi sub j, that pi sub j depends on a weight vector wj. Okay, which is the wj that we are talking about is basically a d plus 1 dimensional vector like this. We are going to have wj0, wj1, etc. until wjd. Okay, so basically for each class, we are going to have a different set of parameters w's. And our goal is to be able to estimate all of these vectors, right? Now, again, similar to the binary logistic regression, because we are looking for probabilities, we cannot just say that P sub j is equal to Wj transpose Xi. We cannot do that because P sub j of Xi. Because this linear relationship is not going to show the characteristics of a probability function. It's not going to be bounded between 0 and 1. So we need to have some function to be able to bound this thing between 0 and 1. So to do this, what we are going to do is that we are going to get some help from the log odd ratio that you remember we have defined for interpretation in the binary logistic regression. So just to remind you, log odd ratio between two classes can be defined as a logarithm of probability of our yi being equal to, for example, class J, Cj, given xi divided by the probability of yi being equal to class, for example, L given xi. Okay, that is our definition of log odd ratio. Now, to make things easier, what we can do is that we can use one class as a base class, and we can define the log odd ratio with respect to that specific class. Okay, so for example, we pick the last class, CK, okay, and we say the log odd ratio for class CJ with respect to class CK is ln of P yi is equal to Cj given xi divided by P yi is equal to Ck given xi for all j's equal to 1 to k. Okay, and from the binary case, you remember that when we calculated the log odd ratio, we saw that 1 unit change in xi has resulted in a linear change in log odd ratio and with the weight of w, right? So if I changed attribute j of our xi 1 unit, the amount that log odd ratio was increased was equivalent to the w parameter corresponding to that attribute j. So basically, we expect the same thing to happen here. So we expect that this whole thing to be equal to wj transpose xi. Wj because the weight vector that is corresponding to class J. And the reason that we pick one class CK here to define the log odd ratios with respect to that one specific class is just to make things easier so that we only use Wj for all of the Js. We don't care about Wks here. Okay? So basically this is going to tell us how much the log odd ratio of class J will go up compared to the baseline class K because of 1 unit change that we have, right? So how much the log of ratio of Cj is going to go up versus Ck for a specific attribute, let's say XL, that is going to be equal to WJL. So this way we can calculate, hopefully, the pi sub j's, right? So let's look at class CK, which is our base class. So for CK, the log odd ratio, if we follow this definition, we are going to have probability of yi is Ck given xi divided by probability of yi is Ck given xi. It should be equal to Wk transpose xi, right? That's what we expect from the definition of log odd ratio. Okay, but also if you look at this, this should be equal to 1, right? And logarithm of 1 is equal to 0. So the first thing that we get out of it is that this Wk transpose xi is always going to be 0 when we select class K as our base class. So from this, we can say that, okay, so for our base class, we are going to set our Wk, the vector of parameters for our base class, to be equal to vector 0. So all of my, so Wk0, Wk0, Wk1 until Wkd, they are all going to be 0. Okay, so for my base class, I have this. Now let's see if I can get the rest of my classes, the pi function for the rest of the classes like that. So we can set Wk to be equal to 0. So basically we have the theta for class K, or the E to Wk, Wk transpose xi to be always equal to 1, right? Because this guy is 0, so E to the 0 is going to be 1. Now, according to that, then, and knowing that the summation of all of my pi j xi's should be equal to 1. Yeah. So if I choose the probability of yi equals to cj given xi to be proportional to e to the wj transpose xi, then I am going to have this ln of pyi being cj given xi over pyi being ck given xi to be equal to ln of e to wj transpose xi over e to, because it is proportional, so the other one is e to wk transpose xi. This we know that is 1, okay? So that is going to be wj transpose xi, right? So this should be proportional to e to the pi sub j of xi should be proportional to e to the wj transpose xi. But also we know that the summation of all of the pi's should be equal to 1, right? So to make that happen, what we are going to do is to normalize these e values. So we are going to say that p sub j of xi is equal to e to wj transpose xi over summation of e to w L transpose xi for L equal to 1 to k. So for all of our classes. So this way, we are going to have summation of pj of xi to be equal to 1 for j equals to 1 to k. And also we do have that log odd ratio thing. So this function is called a softmax function. So basically, what we have done is that we have defined the p sub j of xi function according to the w's. So we have reduced finding a function p sub j that represents our classes to finding a good set of parameters wj's, w1 for class 1, w2 for class 2, etc., etc. And also at the same time, we know that wk, the vector of weights for k, class k, is also equal to 0 always, because we used class k as our base class. Okay, so the softmax, you can think of it as a generalization of the sigmoid function in the binary classifier. Okay, so this is our softmax function. And when k is equal to 2, this is exactly equal to the logistic function. Now, okay, so we decided that we now need to find w's for each class. How are we going to do that? Similar to the binary logistic regression, we are going to do a maximum likelihood estimation, meaning that we are going to define the likelihood of our observed data, and we are going to find a w that maximizes that likelihood. But this time, instead of having one vector of weights w, we have multiple weight vectors w, right? So our data, we said, our data looks like this, augmented data. We have x0, x1 until xt. x0, all of them are ones, and the rest are x1, x2 until xn. So this is our matrix X. And then we have this other class matrix response variable y. So for class 1, class 2, etc., class k, we have that. In each row, we have only one of the variables being equal to 1, the rest are 0. And then our w that we would like to find, we have one w for each class k, right? So if we put all of our w's together, if I put w for class 1, w for class 2, etc., until w for class k together, I am going to have a matrix of parameters or weights w that are basically d plus 1 by k. Also, what we can do is that because we have selected wk as our base class, we only need to find all the values of w until wk minus 1. And we have decided that the weight vector for wk is going to be 0, all 0, right? Okay. So we have a matrix X, we have a matrix Y, and we have a matrix W. Now we are going to define our likelihood L of the likelihood of our data as a function of this matrix W. And this is going to be equivalent to the probability of seeing our Y given our W, right? Okay. So again, with assuming that our data points are all independent of each other, what I'm going to have is a multiplication for each of our data points, I equals to 1 to n, probability of yi given xi and matrix W. Now, just to make things a little bit easier still, what we are going to assume is that our pi i's for our classes are also independent of each other. So basically, this is going to be equivalent, similar to the binary logistic regression that we had this Bernoulli distribution for that. We are going to have this I equals to 1 to n. Now, j equals to 1 to k. So for each of the classes, we have this probability of yi belonging to class cj, right? So basically, this is going to be translated to pi sub j of xi to yij. What is yij? Yij is basically the elements in the Y matrix. So Yij is telling us if for data points I, for Yi, the value for class J is equal to 0 or it is equal to 1, right? So for example, here, this is Y22, it equals to 1. Here, this is Y21, it equals to 0. So it means that our data point number 2 belongs to class 2. So exactly like logistic regression, that when we do take the pj to the power of yij, if the class is 0, this is going to be equal to 1, so it doesn't have any effect in the multiplication. But if yij is equal to 1, we are going to get exactly the probability that xi belongs to class j from it, right? Okay, so this is our likelihood of our observed data given the parameters W. And what we are going to do, again, we are going to take the logarithm of our L of W. which is now going to be translated into logarithm of this multiplication, right? And we are going to optimize for that, right? Okay, so basically this means that if I take the probabilities that we have defined above here for Pij's, what I'm going to have is the logarithm of L of W is going to be equal to logarithm of I equals to 1 to n, j equals to 1 to k, and e to the wj transpose xi over summation of e to L equals to 1 to k, e to WL transpose xi, right, to the power of yij. Okay, so that is going to be the logarithm of our likelihood that we have to define and take the derivative with respect to w's to be able to do gradient ascent algorithm. Now, let's do it for stochastic gradient ascent. So what we can do is to define the derivative of w. Now this is the matrix w, but also we can define it for each of the vectors separately, right? Because not only the data points are independent, but also the classes are independent. So we are going to just find the derivative of our log likelihood with respect to one class j, at data point xi. Okay, at data point xi, because we are going to do stochastic. If we wanted to do batch, for batch, what we would have done was to take the gradient with respect to w, which was the gradient of ln of this w with respect to w. And if we wanted to do batch for each class, we could do the derivative with respect to wj, which was derivative ln of w with respect to wj only, right? But let's do stochastic. If we do the stochastic one and we calculate the gradient, that's basically going to be equal to, if you do it at home, it's going to be equal to yij, so the label, minus pi sub j of xi multiplied by xi. Okay, so if you check our derivative when we had stochastic gradient ascent, in the binary case, you can see that they are basically equivalent to each other. It's the observed yi minus the pi for class 1 of w transpose xi multiplied by xi. So here we also have the same thing. So we have the observed response variable minus pi sub j for that specific class of our data point xi multiplied by xi. Okay, so basically what this gradient means is that when you calculate, when you estimate the probability of xi belonging to class j, if that probability pi is far from by ij, it means that this this value is going to be large, right? And we have to correct for that. We have to correct our vector of weights if we have a big difference here between the observed class being 1 and the probability of data point being actually belonging to that class. And so that's one factor. And also if our input data values are large, we are going to update the weight vectors also with more magnitude. Okay. So basically, the algorithm for multi-class regression is going to look like this. First of all, we have our data as our input, step size again as input, and our stopping criterion value as our input. At the beginning, we are going to augment our data, first of all, for all of our data points, and also we are going to create the yi vectors, the response vectors, so that we can map the categorical values of class labels into vectors, binary vectors of size k. Then we are going to start at iteration 0, and we initialize our W vectors, one vector for each class. For each class, we are going to have one d+1 dimensional vector. And then the rest is very similar to binary logistic regression. So first of all, we are going to keep a copy of WJ transpose for each of our classes. And then in a random order, we go over our data points. Here we are going to have an additional loop, one loop for each class. And for each class, we are going to calculate the pi j of xi, and we are going to calculate the gradient of the vector w for that class at data point xi that we have chosen at random above, and we are going to update the w's accordingly. And after we are done with all of the classes and with all of the data points, then we are going to update the weight of our vector. And then we are going to go to the next epoch or iteration, and we are going to repeat this whole outer iteration until we see that the weight vectors of our classes do not change that much anymore. Now, because we have k different weight vectors, one of the ways to do the stopping criterion is that we can say the summation of changes in all of our weight vectors is going to be less than or equal to epsilon, then we are going to stop. Okay. Now, suppose that we have done this. That's great. So we have a data point. We run a stochastic gradient ascent on maximum likelihood objective, maximum log likelihood objective, and we found the W's for all of our classes. Now someone is giving us a data point. So for example, someone is giving us a weight and a height and a number of legs, and they're asking what class does this data point belong to? So what kind of animal is this? So what we are going to do is to find the class label for that data point, right? So how are we going to do that? What we're going to do is that we know the pi I, right? We know that the pi I is equal to e to the w I transpose that data, right? So we can calculate this for all of our classes. Basically, that is the probability of our data point, z, belongs to class I given data point z, right? We calculate that for all of our classes, and then we are going to see, okay, among all of these classes, which class has the maximum probability. So basically, we are going to choose the class Ci that maximizes this probability across all of the possible classes. And that is going to be our predicted class y hat for that data point.